Alrighty, this video looks at the idea of pressure with depth. That as we change our position in a column of fluid, let's say this could be a container of water, it really wouldn't matter what the fluid was. As we move down, we expect the pressure to increase. As we move up, we expect the pressure to decrease. And the reason, of course, is that as we change our position in the column of fluid, how much weight we have pushing down on us is going to change. So right here, fishy has that much weight or force pushing down on its area. But if fishy moves in down here, he has a lot more weight pushing down on his area. Since force over area is going to give us pressure, well, this fish is going to be subject to higher pressure. Now, the way we look at this in terms of problem solving is by this formula, that the pressure at a certain position in a column of fluid is equal to atmospheric pressure plus the product of the density of the fluid, acceleration due to gravity at that location, and your position in that fluid column. Now, this particular formula, remember, was for absolute pressure. If I wanted gauge pressure, gauge we would subtract from the absolute that atmospheric pressure. So this formula here is actually for absolute pressure. Gauge, I wouldn't have that guy present in the mix. So a typical problem might look something like this. A submarine, I don't draw submarines well, but there's a submarine looking like a large whale, is 120 meters below the surface of the ocean. To what pressure is this guy exposed? Well, he's subject to two fluids. One, the air pushing down on the water, and the water then pushing down on the sub. Now, that's where that P sub 0 comes in. That is atmospheric pressure, an average value for what's going on at sea level, 1.01 times 10 to the 5th Pascal. That pressure is already there. The pressure of the water is the rho GH. And so the combination of the two would tell you the total pressure acting on the sub. So my pressure at depth would be 1.01 times 10 to the 5th Pascal, P sub 0, plus density of seawater, 1025 kilogram per meter cubed on average, and remember densities would be given to you on a test, times gravity, 9.81 meter per second squared, times that depth of 120 meters. And that product right there is my rho GH. And when I solve, I wind up getting, not surprisingly, a nice value, 1.31 times 10 to the 6th Pascal. I've gone down under some water, so I definitely expect it to be larger than the pressure of the air sitting on top of the water. But what happens if I ascend a column of fluid? Let's say instead I happen to be some type of a mountain goat sitting up here on a mountain somewhere 60 meters up from sea level. To what pressure is he exposed? Well, you use the same formula, it's no different. Pressure at a location in a column of fluid, atmospheric plus rho GH. Now in this case we know that as I ascend a column of fluid, pressure goes down. And the pressure I'm looking at is going to be air pressure. And this value, P sub 0, is right here, at the bottom of the mountain. So since I'm going up from the bottom of the mountain, I know my pressure is going to be less than my 1.01 times 10 to the 5th. Well, in the last example, when we worked with rho GH, I just plugged in 9.81 meter per second squared here and 120 here. And that gave us, of course, a positive product to add to P sub 0. Well, if we really think about it in a slightly more, I guess, appropriate fashion, getting all our sign conventions in place, my density of my seawater, of course, would be positive, but gravity technically would be negative because it is downward. And the displacement was also downward. So if I was really to write it a little bit more appropriately, the phrase would have looked like this. Did it make a difference in the value? No. Negative times negative is positive. But for a problem like our little mountain goat, I do have to take some precautions, because I know in this case I don't want a positive ρGH product. I need it to be negative. Why? Because I have to turn around and subtract him from my P sub 0. Since my formula stipulates adding, what I have to add is a negative. So you might think of it this way. My density of air will still be positive, but you might now want to think about the fact that gravity would be negative, and a height now above the 0 level, i.e. the base of the mountain, would be positive. Putting my information into my problem, atmospheric pressure, 1.01 times 10 to the 5th Pascal, plus density of air, 1.29 kilogram per meter cubed, gravity, I'm just going to write G because why not, and we can go ahead and make him a little negative G if we want to. Our height, a positive 60 meters. Our ρGH will be negative, which when added to the value for atmospheric pressure will give me a pressure above sea level, something lower. And when I put my numbers in, I wind up getting basically 1 times 10 to the 5th Pascal. Not a lot lower than 1.01 times 10 to the 5th, I'll grant you, but we're really not that high up, and the density of air is really small. So when we're working with problems dealing with pressure at depth, as I go down a column of fluid, and for our purposes it's going to be probably going down into some form of a liquid, atmospheric pressure will add to the pressure of the fluid, so that my pressure at a certain point will be greater than atmospheric. However, when I go up a fluid, like climbing on top of a mountain there, my pressure here versus here, I'm going to have a different story. That pressure is going to be lower than atmospheric. So I'll need to take that atmospheric and subtract my ρGH product. And if I think about the signs, it'll come out the way I want it to come out. So make sure you can solve a problem regardless of what the fluid is, and you would be given density. Whether we go down a fluid, up in a fluid, you will of course be given the density value, so don't worry about having to deal with that. Only trick you might have to consider is, do they ask you for absolute or gauge? Absolute pressure, we go ahead and add the P sub 0. If it's gauge pressure, we do not.